Today, we're embarking on an extraordinary journey through time and space. Our mission? To unravel the captivating story of how scientists discovered the first planets beyond our solar system, the exoplanets. Imagine for a moment the vastness of our universe. Billions of galaxies, each containing billions of stars. For centuries, humanity has gazed at the night sky, wondering if other worlds exist out there. Are we alone? Or is our planet just one of countless others, orbiting distant suns? This quest to find other worlds is not just a tale of scientific discovery. It's a story of human perseverance, ingenuity, and relentless curiosity. It's about pushing the boundaries of our technology and our imagination. From the first speculations of ancient philosophers to the cutting-edge instruments of modern astronomy, we've been driven by an insatiable desire to understand our place in the cosmos. But here's a mind-bending thought to kick off our journey. The first confirmed exoplanets weren't found around stars like our Sun. They were discovered in a place so extreme, so violent, that it challenged everything we thought we knew about planetary formation. Want to know where? Stay tuned, because in the next few minutes, you're about to have your cosmic mind blown. If you're ready to expand your universe and join us on this exoplanet expedition, don't forget to hit that like button right now. It helps more cosmic explorers like you find our channel. And if you want to stay updated on all our celestial adventures, smash that subscribe button and ring the notification bell. Welcome aboard the Exploring the Universe starship, your portal to the wonders of the cosmos. The concept of worlds beyond our solar system is far from a modern idea. In fact, it has roots that stretch back to ancient times, demonstrating humanity's enduring fascination with the possibility of other worlds. Let's journey back to ancient Greece, where the seeds of exoplanet speculation were first sown. In the 4th century BCE, the philosopher Epicurus proposed a revolutionary idea for his time. In a letter to Herodotus, he wrote, "There are infinite worlds both like and unlike this world of ours. We must believe that in all worlds there are living creatures and plants and other things we see in this world." Epicurus wasn't alone. Other Greek thinkers like Democritus and Lucretius also entertained the notion of multiple worlds. These early speculations, while not based on scientific evidence, laid the groundwork for future cosmic explorations. Fast forward to the Renaissance, and we encounter one of the most daring thinkers of his time, Giordano Bruno. In 1584, Bruno published On the Infinite Universe and Worlds, where he boldly declared, "There are countless suns and countless Earths all rotating around their suns in exactly the same way as the 7 planets of our system." Bruno's vision was truly revolutionary. He suggested that the stars we see in the night sky are distant suns, much like our own, and that these suns might host their own planets. This idea was so radical and contrary to the dominant worldview that it contributed to Bruno's eventual execution by the Roman Inquisition in 1600. As we enter the Age of Enlightenment, we find 2 intellectual giants contemplating the formation of planets around other stars, Isaac Newton and Immanuel Kant. Isaac Newton, renowned for his laws of motion and universal gravitation, pondered the possibility of other planetary systems. In his seminal work, Principia Mathematica, 1687, Newton's laws implicitly suggested that the same forces governing our solar system could be at work around other stars. Immanuel Kant, the influential philosopher, took these ideas further. In his 1755 work, Universal Natural History and Theory of the Heavens, Kant proposed what we now call the nebular hypothesis. He suggested that our solar system formed from a large cloud of gas and dust, and importantly, he extended this idea to other stars. In the same way, then, as our solar system was produced, so have the other planetary systems been formed, and so have all the orders of worlds been produced, which fill the celestial space to an extent that cannot be limited. Kant's theory was groundbreaking, proposing not only the existence of exoplanets but also a mechanism for their formation that's strikingly similar to modern theories. These early speculations, from ancient Greece to the Enlightenment, showcase the human imagination's power to conceive of possibilities beyond our immediate experience. They laid the philosophical and theoretical groundwork for the scientific search for exoplanets that would begin in earnest centuries later. As we transition from philosophical speculation to scientific inquiry, we enter an era of ambitious attempts to detect exoplanets. These early efforts, while ultimately unsuccessful, laid crucial groundwork for future discoveries and highlighted the immense challenges involved in identifying worlds beyond our solar system. Our journey begins in 1855 with Captain William Stephen Jacob, a British astronomer working at the Madras Observatory in India. Jacob made a bold claim that sent ripples through the astronomical community. He reported observing orbital perturbations in the binary star system 70 Ophiuchi. Jacob's logic was sound. If a massive object, like a planet, were orbiting one of the stars, it should cause slight irregularities in the star's orbits. This method, known as astrometry, was one of the earliest proposed techniques for exoplanet detection. There is no room to doubt that the plane of motion of the third body is inclined to the visual ray at a considerable angle. The mass of the third body would be about 3.2 times that of Jupiter. While Jacob's claim was later disproven, his work represents one of the first systematic attempts to detect an exoplanet using scientific methods. It highlighted the potential of using stellar motion as an indirect means of planet detection, a concept that would prove crucial in future discoveries. Fast forward to 1943, and we encounter another significant claim in the history of exoplanet detection. Kai Strand, a Danish astronomer working at the Sproul Observatory in Pennsylvania, announced the potential discovery of a planet orbiting the star 61 Cygni. Using improved astrometric techniques, Strand observed what he believed to be wobbles in the motion of 61 Cygni, similar to what Jacob had reported nearly a century earlier. Strand estimated that the proposed planet had a mass about 16 times that of Jupiter, orbiting with a period of roughly 4.9 years. The observations of 61 Cygni obtained with the Sproul refractor since 1914 reveal the presence of a perturbation in the motion of this visual binary star, which can be represented by a period of about 4.9 years. This claim generated considerable excitement in the astronomical community. However, like Jacob's earlier assertion, Strand's planet would eventually be refuted as more precise measurements became available. The decades following Strand's claim saw a flurry of reported exoplanet detections, all of which would ultimately be disproven. This period serves as a testament to both the difficulty of exoplanet detection and the eagerness of the scientific community to make this groundbreaking discovery. Van de Camp, a Dutch astronomer, claimed to have detected 2 planets orbiting Barnard's star using astrometry. His work spanned several years and garnered significant attention. However, subsequent studies failed to confirm his findings. Donald W. Aitken and colleagues reported evidence of planetary companions to these stars based on perturbations in their proper motions. These claims, too, were later refuted. Throughout the 1980s, several announcements were made of substellar companions to nearby stars. While not technically planets, these objects were thought to bridge the gap between planets and stars. Most of these claims were later withdrawn or disproven. While it might seem discouraging that all these early attempts failed, they played a crucial role in the development of exoplanet science. They highlighted the extreme precision required for exoplanet detection, spurring the development of more sensitive instruments and techniques. These attempts kept the search for exoplanets at the forefront of astronomical research, maintaining interest and funding in this area. The process of disproving these claims helped refine our understanding of stellar behavior and the various factors that can mimic the presence of an exoplanet. These early efforts laid the groundwork for the eventual successful detection methods, including the refinement of astrometry and the development of new techniques like the radial velocity method. As we've seen, the search for exoplanets was fraught with difficulties and false starts. But why exactly was it so challenging to detect these distant worlds? Let's dive into the formidable obstacles that astronomers faced in their quest to find planets beyond our solar system. Imagine trying to spot a firefly hovering next to a lighthouse beam from hundreds of miles away. This analogy gives us a sense of the extreme brightness difference between a star and its orbiting planets. Our Sun is roughly 1 billion times brighter than Jupiter, the largest planet in our solar system. For an Earth-like planet, this ratio is even more extreme, about 10 billion to 1. Dr. Sarah Seeger, a pioneering exoplanet researcher, explains it this way. It's like trying to see a moth flying around a streetlight in Los Angeles, from New York City. This vast difference in luminosity means that the light from an exoplanet is easily lost in the glare of its host star, making direct observation incredibly challenging. Not only are exoplanets dim compared to their stars, but they also appear extremely close to their stellar hosts from our vantage point on Earth. If you were to observe our solar system from 30 light-years away, a relatively close distance in galactic terms, the Earth would appear to be separated from the Sun by only 1 arcsecond, that's January 3600th of a degree in the sky. For comparison, the full moon as seen from Earth spans about 1800 arcseconds. Given these challenges, astronomers turn to indirect methods of detection. However, the effects that planets have on their host stars are incredibly subtle. A planet's gravity causes its star to move in a small circle or ellipse. For an Earth-like planet orbiting a Sun-like star, this wobble is tiny, causing movements of about 9 centimeters per second in the star's velocity. Even for a Jupiter-sized planet, the effect is only about 12.5 meters per second. When a planet passes in front of its star, It blocks a tiny amount of the star's light. An Earth-sized planet transiting a Sun-sized star blocks only about 0.01% of the star's light. This is equivalent to the dimming caused by a fruit fly passing in front of a car's headlight. Earth's atmosphere poses another significant challenge. It distorts and blurs the light from distant stars, making precise measurements even more difficult. This is why many of our most powerful telescopes are now placed in space, above the atmosphere. The precision required to detect exoplanets pushed the boundaries of technology. Spectrographs needed to measure stellar wobbles with a precision of 1 meter per second or better. Photometers had to detect changes in stellar brightness of less than 0.01%. Adaptive optics and interferometry techniques had to be developed to overcome atmospheric distortions. As we've seen, finding exoplanets is an enormously challenging task. To overcome these obstacles, astronomers developed several ingenious methods. Let's explore the 3 primary techniques that paved the way for the first exoplanet discoveries. Astrometry is one of the oldest methods used in the search for exoplanets. Dating back to the 19th century, astrometry measures the precise position of a star in the sky over time. If a planet is orbiting the star, its gravitational pull will cause the star to wobble slightly. This wobble appears as a tiny periodic shift in the star's position against the background of more distant stars. The wobble is incredibly small. For a Jupiter-mass planet orbiting a Sun-like star at $1, the star's motion is only about the width of a human hair seen from 10 miles away. Earth's atmosphere distorts stellar positions, making precise measurements difficult from the ground. Long-term observations, often years, are required to detect the periodic nature of the wobble. While astrometry led to many early claims of exoplanet detections, most were later refuted. However, the method remains valuable, especially with space-based telescopes like Gaia, which can achieve the necessary precision. The radial velocity method, also known as Doppler spectroscopy, became the first technique to reliably detect exoplanets around main sequence stars. As a planet orbits a star, it causes the star to move in a small circle or ellipse. When the star moves towards Earth, its light is slightly blue-shifted. When it moves away, the light is red-shifted. By measuring these periodic shifts in the star's spectrum, astronomers can infer the presence of a planet. We're essentially listening to the star's voice. The planet's gravity causes the star's voice to waver, alternating between slightly higher and lower pitches. It can detect planets that don't transit their star. It provides information about the planet's minimum mass and orbital period. The velocity changes are tiny, often just a few meters per second. It's most sensitive to large planets close to their stars, leading to an initial bias towards detecting hot Jupiters. The radial velocity method led to the discovery of 51 Pegasi b in 1995, opening the floodgates for exoplanet detections. Surprisingly, the first confirmed exoplanets were found not around a normal star, but a pulsar, the remnant of a supernova explosion. Pulsars emit radio waves with extraordinary regularity, like cosmic lighthouses. If a planet is orbiting the pulsar, it causes tiny variations in the arrival times of these pulses. By precisely measuring these timing variations, astronomers can deduce the presence of planets. Pulsars are nature's most precise clocks. A planet's gravity causes the pulsar to move ever so slightly, making its signals arrive a bit earlier or later than expected. Extremely sensitive, can detect even Earth-mass planets. Pulsars' reliable signals allow for very precise measurements, only applicable to pulsars, which are relatively rare. Planets around pulsars are unlikely to be habitable due to the extreme environment. This method led to the groundbreaking discovery of 2 planets orbiting the pulsar PSRB 1257+12 in 1992, marking the first confirmed exoplanet detection. These 3 methods, astrometry, radial velocity, and pulsar timing, represent the vanguard of exoplanet detection techniques. Each has its strengths and limitations, and together they laid the foundation for the exoplanet revolution. The year 1992 marks a pivotal moment in astronomy, ushering in the era of exoplanets. After decades of speculation and unsuccessful searches, astronomers finally confirmed the existence of planets beyond our solar system. Let's delve into these groundbreaking discoveries that forever changed our understanding of the universe. On January 9, 1992, astronomers Alexander Woolston and Dale Frail published a paper in Nature announcing an extraordinary discovery. 2 planets orbiting the pulsar PSRB 1257+12, located about 2,300 light-years from Earth. Using the Arecibo radio telescope in Puerto Rico, Woolson and Frail detected tiny variations in the arrival times of radio pulses from PSRB 1257+12. These variations indicated the presence of two planets, with masses of 4.3 and 3.9 times that of Earth, orbiting the pulsar every 66.6 and 98.2 days, respectively. A third, smaller planet was later confirmed in 1994. This discovery was groundbreaking for several reasons. It provided the first unambiguous evidence of planets outside our solar system. It demonstrated that planets could form or survive in the harsh environment around a pulsar. It suggested that planetary systems might be more common and diverse than previously thought. The discovery was particularly startling because pulsars are the remnants of massive stars that have exploded as supernovae. The fact that planets could exist around such an object challenged existing theories of planetary formation and survival. While the pulsar planets were a monumental discovery, astronomers were eager to find planets around stars more similar to our Sun. This dream was realized on October 6, 1995, when Michel Mayor and Didier Queloz of the University of Geneva announced the discovery of 51 Pegasi b. Using the radial velocity method at the Observatoire de Haute Provence in France, Mayor and Queloz detected a planet orbiting the star 51 Pegasi, about 50 light-years from Earth. The planet, dubbed 51 Pegasi b, has a mass about half that of Jupiter and orbits its star every 4.2 days. It was the first exoplanet found orbiting a main sequence star like our Sun. It opened the floodgates for exoplanet detections, proving that the radial velocity method could reliably find planets. The planet's characteristics challenged existing theories of planetary formation. 51 Pegasi b was unlike anything in our solar system, a gas giant orbiting extremely close to its star, completing an orbit in just over 4 days. This type of planet, soon dubbed a hot Jupiter, was not predicted by planetary formation theories of the time. The discovery of 51 Pegasi b had an enormous impact. It sparked a race to find more exoplanets, leading to a rapid increase in detections. It prompted the development of new theories of planetary formation and migration. It captured the public imagination, bringing the search for exoplanets into the spotlight. These two discoveries in 1992 and 1995 marked the beginning of a new era in astronomy. They proved conclusively that our solar system was not unique in the universe and opened up a whole new field of study. The groundbreaking discoveries of the early 1990s opened the floodgates for exoplanet research. What followed was a period of rapid advancement and exciting discoveries that transformed our understanding of planetary systems. Let's explore this revolutionary period in more detail. Following the discovery of 51 Pegasi b, astronomers around the world began intensively searching for more exoplanets. Their efforts quickly bore fruit. By the end of 1996, 7 exoplanets had been confirmed. By 2000, this number had grown to over 50. Most of these early discoveries were hot Jupiters, gas giants orbiting very close to their stars. This bias was due to the limitations of the radial velocity method, which more easily detects large planets in short orbits. Key discoveries of this period included Upsilon Andromedae b, c, and d, 1996 to 1999, the first multi-planet system discovered around a main sequence star. Gliese 876 b, 1998, the first planet discovered around a red dwarf star. These findings began to reveal the diversity of exoplanetary systems, hinting at the incredible variety we would later uncover. On November 5, 1999, astronomers announced a significant breakthrough: the first detection of an exoplanet by the transit method. HD 209458b, a hot Jupiter already known from radial velocity measurements, was observed passing in front of its star. This transit caused a tiny but measurable dip in the star's brightness. This discovery was crucial for several reasons. It provided independent confirmation of the planet's existence. It allowed for precise measurements of the planet's size and density. It opened up new avenues for studying exoplanet atmospheres. The transit method would go on to become one of the most productive techniques for finding exoplanets, especially with the launch of space-based observatories like Kepler. Building on the transit discovery, astronomers achieved another milestone in 2001, the first detection of an atmosphere around an exoplanet. Using the Hubble Space Telescope, a team led by David Charbonneau observed HD 209458b during transit. They detected the signature of sodium in the planet's atmosphere. We could study the composition of exoplanet atmospheres. Our techniques were becoming sensitive enough to detect specific elements on distant worlds. This capability would later prove crucial in the search for potentially habitable planets. While most exoplanets were detected indirectly, Astronomers had long dreamed of actually seeing these distant worlds. In 2004, this dream began to become a reality. On September 10, 2004, astronomers announced the first direct image of what appeared to be an exoplanet. The object, designated 2M1207b, was observed orbiting a brown dwarf about 170 light-years from Earth. The planet's existence was confirmed in 2005 through further observations. This achievement was groundbreaking because it provided the first visual confirmation of an exoplanet. It allowed for direct study of the planet's physical properties. It demonstrated the potential of direct imaging techniques. While 2M1207b was an unusual case, a very large planet orbiting a brown dwarf, it paved the way for future direct imaging efforts. These developments in the late 1990s and early 2000s marked the beginning of the exoplanet revolution. Each discovery brought new surprises and challenged our understanding of planetary systems. The exponential growth in exoplanet discoveries didn't happen by chance. It was the result of several key technological breakthroughs that revolutionized our ability to detect and study these distant worlds. Let's explore the crucial advances that enabled the exoplanet boom. One of the most significant advances came in the form of increasingly precise spectrographs, with HARPS leading the way. HARPS, installed on the ESO's 3.6M telescope in La Silla, Chile, in 2003, represented a quantum leap in radial velocity measurements. Dr. Didier Queloz, one of HARPS' creators, explains, HARPS can detect stellar wobbles as small as 1 meter per second. That's like measuring the speed of a snail from hundreds of light-years away. Extremely high spectral resolution, R is almost equal to 115,000. Exceptional wavelength stability, less than 1 meter per second over months to years. Vacuum-sealed and temperature-controlled environment. The impact was immediate and profound. HARPS alone has been responsible for discovering hundreds of exoplanets, including many in the super-Earth category. Charge-coupled devices are the digital film of modern astronomy. Advances in CCD technology have been crucial for the transit method of exoplanet detection. Increased quantum efficiency, ability to convert photons to electrical signals. Reduced noise levels. Larger array sizes, allowing for wider fields of view. These improvements enabled missions like Kepler, which used a 95-megapixel CCD array to monitor over 150,000 stars simultaneously, leading to thousands of exoplanet discoveries. Placing telescopes in space, above the distorting effects of Earth's atmosphere, has been a game-changer for exoplanet research. While not designed for exoplanet research, HST has made significant contributions, including the first detection of an exoplanet atmosphere in 2001. Launched in 2003, Spitzer's infrared capabilities allowed it to study exoplanet atmospheres and even create rudimentary weather maps of some gas giants. Launched in 2009, Kepler revolutionized exoplanet discovery using the transit method, finding thousands of new worlds. Launched in 2018, TESS is surveying the entire sky, focusing on nearby bright stars, making follow-up studies easier. As our instruments became more sophisticated, so did the methods for processing and analyzing the data they produce. This technique corrects for atmospheric distortion in real time, allowing ground-based telescopes to approach space-based image quality. By blocking out the light from a star, coronagraphs allow telescopes to see much fainter nearby objects, like planets. Advanced statistical techniques help astronomers tease out the faint signals of exoplanets from noisy data. More recently, machine learning and artificial intelligence have begun to play a crucial role in exoplanet research. Automated detection of transit signals in large datasets. Classification of exoplanet candidates. Analysis of spectral data to determine atmospheric composition. These technological advances have transformed exoplanet science from a niche field to one of the most exciting and rapidly progressing areas of astronomy. Dr. Sarah Seeger, a leading exoplanet researcher, summarizes, each of these advances has opened new windows into the exoplanet universe. Together, they've turned the discovery of exoplanets from a rare event into an everyday occurrence, bringing us closer to answering fundamental questions about our place in the cosmos. The dawn of the 21st century marked a new era in the search for exoplanets. For the first time, space agencies began launching missions dedicated specifically to the hunt for worlds beyond our solar system. These missions revolutionized our understanding of planetary systems and firmly established exoplanet research as a cornerstone of modern astronomy. COROT holds the distinction of being the first space mission dedicated to searching for exoplanets. Its primary methods were asteroseismology, studying stellar oscillations, and the transit method. Launch date: December 27, 2006. Agency: NIS, French Space Agency, in collaboration with ESA and other international partners. First space-based exoplanet detection. Discovered about 30 confirmed exoplanets. Provided crucial insights into stellar physics. One of Corot's most significant discoveries was Corot 7b, the first confirmed rocky exoplanet. This finding hinted at the existence of a new class of planets, super-Earths. Despite technical issues leading to its decommissioning in 2013, Corot paved the way for future exoplanet hunting space missions. The Kepler mission marked a quantum leap in our ability to detect exoplanets and revolutionized our understanding of their prevalence and diversity. Launch date: March 7, 2009. Agency: NASA. Primary mission lasted 3.5 years. Extended to 9 years. Continuously monitored over 150,000 stars in a fixed field of view. Used the transit method to detect exoplanets. Discovered over 2,600 confirmed exoplanets. Revealed that planets are common in our galaxy. Found the first Earth-sized planet in the habitable zone of a star, Kepler 186f. Some of Kepler's most notable discoveries include Kepler 16b, the first confirmed circumbinary planet, orbiting 2 stars. Kepler 22b, the first planet in the habitable zone of a Sun-like star. Kepler 90, a star system with 8 planets, rivaling our own solar system in complexity. After its primary mission, Kepler continued as K2, surveying different areas of the sky until it ran out of fuel in 2018. The wealth of data from Kepler continues to yield new discoveries even years after the mission's end. TESS is the spiritual successor to Kepler, designed to survey a much larger portion of the sky and focus on nearby, bright stars. Launch date: April 18, 2018. Agency: NASA. 2-year primary mission. Extended indefinitely. Surveys 85% of the sky, divided into 26 sectors. Uses transit method, like Kepler, but with a focus on M-dwarf stars. 4 wide-field cameras that simultaneously watch large swaths of the sky. Ability to detect planets ranging from Earth-size to gas giants. Focus on stars 30 to 100 times brighter than those Kepler observed, making follow-up easier. Dr. George Ricker, TESS principal investigator, explains the mission's significance. TESS is the next step in the search for planets outside of our solar system, including those that could support life. The mission will find exoplanets that will become targets for future telescopes to characterize their atmospheres and, ultimately, look for signs of life. Notable achievements: as of 2024, discovery of over 5,000 exoplanet candidates. Confirmation of hundreds of new exoplanets. Detection of several potentially habitable worlds. Some of TESS's exciting discoveries include TOI 700d, one of the first Earth-sized planets in the habitable zone discovered by TESS. LHS 3844b, a rocky super-Earth that may lack an atmosphere. HD 21749c, one of the smallest planets found by TESS, only slightly larger than Earth. These dedicated exoplanet hunting missions have transformed our understanding of the universe. Dr. Sarah Seeger, an exoplanet researcher and TESS team member, summarizes, "Before these missions, we could only speculate about the prevalence of planets in our galaxy. Now, we know that planets are everywhere. These missions have taken us from asking, are there other planets? To which of these planets might harbor life?" The data from Corot, Kepler, and TESS have not only yielded thousands of new worlds, but also provided crucial statistical information about the distribution and characteristics of planetary systems. This information is helping shape our theories of planet formation and evolution, and guiding the design of future missions aimed at characterizing exoplanet atmospheres and searching for signs of life. As we look to the future, missions like JWST and Plato promise to build on this legacy, pushing our ability to study exoplanets to new heights. The era of dedicated exoplanet missions has truly ushered in a golden age of planetary discovery. The field of exoplanet research has been marked by a series of groundbreaking discoveries that have reshaped our understanding of planetary systems and our place in the universe. Let's explore some of the most notable recent milestones that have captivated both scientists and the public imagination. Kepler 16b, the first confirmed circumbinary planet, 2011. Discovery date: September 15, 2011. Nickname: Tatooine, after Luke Skywalker's home planet in Star Wars. Kepler 16b marked a significant milestone as the first confirmed planet orbiting two stars, known as a circumbinary planet. This discovery proved that stable planetary orbits are possible in binary star systems, expanding our understanding of where planets can form and exist. Mass: about 0.33 Jupiter masses. Orbit: circles both stars every 229 days. Temperature: estimated at -100 degrees Celsius to -70 degrees Celsius. The discovery of Kepler 16b opened up a new frontier in exoplanet research, leading to the subsequent discovery of many more circumbinary planets. Kepler 186f, first Earth-sized planet in the habitable zone, 2014. Discovery date: April 17, 2014. Kepler 186f represented a major milestone in the search for potentially habitable worlds. It was the first validated Earth-sized planet orbiting within the habitable zone of another star, where liquid water could potentially exist on the surface. Size: about 1.1 times the radius of Earth. Orbit: 130-day orbit around a red dwarf star. Distance: about 500 light-years from Earth. Dr. Elisa Quintana, the lead author of the discovery paper, explained the significance. Kepler 186f is the first validated Earth-sized planet in the habitable zone of another star. It's a landmark on the road to discovering habitable planets. This discovery was a crucial step towards finding a true Earth analog and demonstrated that Earth-sized planets in habitable zones are not just theoretical possibilities but actually exist in our galaxy. Proxima Centauri b, the closest exoplanet to Earth, 2016. Discovery date: August 24, 2016. The discovery of an Earth-sized planet orbiting Proxima Centauri, the closest star to our solar system, was a monumental event in exoplanet research. At just 4.2 light-years away, Proxima Centauri b became the closest known exoplanet to Earth, igniting dreams of future interstellar exploration. Mass: at least 1.3 times that of Earth. Orbit: 11.2-day orbit within the star's habitable zone. Star type: red dwarf. Dr. Guillaume Anglade-Rescued, who led the discovery team, stated, "The search for life on Proxima b comes next." Proxima Centauri is a very small and cool star, but its planet might still be habitable if it has an atmosphere and liquid water on its surface. This discovery not only provided a tantalizing nearby target for future studies, but also suggested that the nearest stars to us are promising places to look for exoplanets. TRAPPIST-1, a system of 7 Earth-sized planets, 2017. Discovery date: February 22, 2017. The announcement of the TRAPPIST-1 system marked one of the most exciting discoveries in exoplanet history. This system of 7 Earth-sized planets orbiting a single star captured the world's imagination and provided an unprecedented opportunity to study potentially habitable worlds. Star: ultra-cool dwarf star, about 8% the mass of the Sun planets. 7 planets, all approximately Earth-sized. Distance: about 40 light-years from Earth. 3 of the planets, E, F, and G, orbit in the star's habitable zone. Dr. Michael Gillen, the lead researcher, expressed the excitement surrounding this discovery. "This is an amazing planetary system, not only because we have found so many planets, but because they are all surprisingly similar in size to the Earth." The TRAPPIST-1 system is particularly exciting for several reasons. The sheer number of Earth-sized planets in one system. The potential for multiple habitable worlds in a single system. The proximity of the system, making detailed follow-up studies possible. Dr. Nicole Lewis, an astronomer involved in studying the system, added, "The TRAPPIST-1 system provides one of the best opportunities in the next decade to study the atmospheres of potentially habitable Earth-sized planets. These recent milestones have dramatically expanded our understanding of planetary systems and brought us closer to answering fundamental questions about the prevalence of habitable worlds and the potential for life beyond Earth." Dr. Sarah Seeger, a prominent exoplanet researcher, summarizes the impact of these discoveries. "Each of these milestones represents a significant step in our journey to understand our place in the cosmos. From worlds with 2 suns to potentially habitable planets right in our cosmic backyard, these discoveries are rewriting our understanding of planetary formation and evolution. They're also bringing us tantalizingly close to answering the age-old question: are we alone in the universe? As our technology and methods continue to improve, we can expect even more groundbreaking discoveries in the coming years. The next generation of telescopes and missions, both ground-based and space-based, promise to push the boundaries even further, potentially allowing us to detect biosignatures on distant worlds and maybe, just maybe, find signs of life beyond our solar system. As we stand in 2024, the field of exoplanet research has undergone a remarkable transformation. From the first confirmed discovery in 1992 to today, we've witnessed an explosion of knowledge that has fundamentally altered our understanding of planetary systems and our place in the universe. As of the latest data from NASA's Exoplanet Archive, confirmed exoplanets, over 5,000. Candidate exoplanets awaiting confirmation, several thousand. The diversity of these discovered worlds is staggering, ranging from hot Jupiters, massive gas giants orbiting extremely close to their stars, super-Earths, planets larger than Earth but smaller than Neptune, mini-Neptunes, gas-rich planets smaller than Neptune, Earth-sized planets, some in the habitable zones of their stars. While the discovery of new exoplanets continues at a rapid pace, the field is increasingly shifting towards characterizing these worlds. This marks a new phase in exoplanet science, moving from "are they there?" to "what are they like?" Using spectroscopy, scientists are beginning to analyze the atmospheres of some exoplanets. This can reveal the presence of water vapor, methane, and other molecules, potential biosignatures that could indicate the presence of life. For some larger exoplanets, scientists are creating rudimentary weather maps by observing temperature variations across the planet's surface. By combining a planet's mass and radius data, researchers can infer its density and make educated guesses about its internal structure. For planets in the habitable zone of their stars, scientists are developing models to assess their potential to support life as we know it. Several cutting-edge technologies and missions are propelling this new era of exoplanet characterization. Launched in 2021, JWST's unprecedented infrared capabilities are allowing for detailed atmospheric studies of exoplanets. Set to begin operations in the mid-2020s, this ground-based telescope will have the power to directly image smaller, rocky exoplanets. Scheduled for launch in 2026, Plato will search for and study Earth-sized planets in habitable zones around Sun-like stars. Perhaps the most exciting aspect of current exoplanet research is the hunt for signs of life beyond Earth. This interdisciplinary effort combines astronomy, biology, geology, and chemistry. Refinement of potential biosignatures that could indicate the presence of life. Development of techniques to distinguish between biotic and abiotic sources of atmospheric gases. Consideration of exotic forms of life that might exist in environments very different from Earth. Despite the tremendous progress, significant challenges remain. Detecting and characterizing Earth-like planets around Sun-like stars. Distinguishing between false positives and genuine biosignatures. Understanding the full range of factors that contribute to planetary habitability. The current state of exoplanet research is one of rapid progress and tantalizing possibilities. We've moved from the era of pure discovery into a new phase of detailed characterization and the hunt for potentially habitable worlds. As we continue to refine our techniques and deploy new technologies, we stand on the brink of potentially answering one of humanity's most profound questions. Are we alone in the universe? The journey of exoplanet discovery, from theoretical speculation to the current era of characterization and the search for life, represents one of the most exciting scientific adventures of our time. As we look toward the horizon of exoplanet science, we find ourselves on the cusp of a new era. The future promises unprecedented technological advancements and scientific breakthroughs that will revolutionize our understanding of worlds beyond our solar system. Let's explore the key areas that will shape the future of exoplanet research. The advent of next-generation telescopes will dramatically enhance our ability to detect and study exoplanets. Launched in 2021, JWST represents a quantum leap in our ability to study exoplanet atmospheres. Unprecedented infrared sensitivity, ability to probe the atmospheres of smaller rocky planets, potential to detect biosignatures in exoplanet atmospheres. Set to begin operations in the mid-2020s, the ELT will be the world's largest optical/near-infrared telescope, 39.3-meter primary mirror, adaptive optics for sharp imaging, ability to directly image rocky exoplanets. Future space missions will focus specifically on studying exoplanet atmospheres in unprecedented detail. Planned for launch in 2029, Ariel will be the first space mission dedicated to measuring the chemical composition and thermal structures of exoplanet atmospheres. Mission goals: survey about 1,000 exoplanets, create a chemical census of exoplanet atmospheres, investigate links between planet chemistry and formation, LUVOIR or HAB-X. These proposed NASA missions aim to characterize a wide range of exoplanets, including potentially habitable ones. Potential capabilities: direct imaging of Earth-like exoplanets, detailed spectroscopic analysis of exoplanet atmospheres, search for biosignatures. The holy grail of exoplanet research is the detection of life beyond Earth. Future efforts will focus intensively on this goal. Scientists are working to improve our ability to detect and interpret potential signs of life in exoplanet atmospheres. Researchers are broadening their understanding of the conditions that could support life. Novel technologies are being developed to enhance our ability to detect subtle signs of life. The ability to directly image Earth-like exoplanets represents one of the most exciting prospects for future exoplanet research. These devices block out the light from a star, allowing the detection of much fainter planets. Massive, flower-shaped structures flown in formation with a space telescope to block starlight. The coming decades of exoplanet research promise to be transformative. Dr. Natalie Batalha, a leader in exoplanet science, summarizes the potential impact. We're on the verge of a new era in our understanding of planetary systems and our place in the cosmos. The ability to characterize Earth-like worlds, to probe their atmospheres for signs of life, and to potentially image these distant planets directly. These capabilities will fundamentally reshape our perspective on the universe and our role within it. As we look to the future, key questions that may be answered include: how common are Earth-like planets in the galaxy? What is the diversity of planetary atmospheres and climates? Are we alone in the universe? Or is life common? Could we detect signs of intelligent life or technological civilizations? Dr. David Charbonneau, a prominent exoplanet researcher, offers a final thought. The next few decades of exoplanet research have the potential to answer questions that humans have pondered for millennia. Whether we find life beyond Earth or not, the journey of discovery will undoubtedly reshape our understanding of our cosmic home and our place within it. It's an incredibly exciting time to be an exoplanet scientist. And indeed, to be human. The future of exoplanet research stands as one of the most promising and potentially transformative areas of scientific inquiry. As we continue to push the boundaries of our technological capabilities and scientific understanding, we edge ever closer to answering some of the most profound questions about our existence and our place in the vast cosmic tapestry. The history of exoplanet discovery stands as a testament to human ingenuity and our relentless quest to understand our place in the universe. From philosophical speculations to revolutionary discoveries, each step has brought us closer to answering the age-old question: are we alone in the universe? This journey of discovery has been nothing short of extraordinary. It began with the musings of ancient philosophers who dared to imagine worlds beyond our own, gained momentum through the scientific revolution, and exploded into a new frontier of astronomy in the late 20th and early 21st centuries. The path of exoplanet research has been marked by perseverance, innovation, and collaboration. Scientists have overcome immense challenges, developing increasingly sophisticated methods to detect and study these distant worlds. From the first confirmed discovery of exoplanets orbiting a pulsar in 1992 to the thousands of confirmed exoplanets we know today, each discovery has expanded our understanding of the cosmos. This field has not only revolutionized our knowledge of planetary systems, but has also profoundly impacted our perspective on our own place in the universe. Dr. Sarah Seeger, a pioneering exoplanet researcher, reflects on this impact. The discovery of exoplanets has fundamentally changed our view of the cosmos. We've gone from wondering if planets exist around other stars to realizing that planets are common, diverse, and in many ways unlike anything we imagined. This journey has humbled us, showing that our solar system is just one among countless others, each with its own unique characteristics. The search for exoplanets has also reignited humanity's age-old question about the existence of life beyond Earth. As we've discovered potentially habitable worlds and developed the means to study their atmospheres, we've opened up real possibilities for detecting signs of life on other planets. As we look to the future, the field of exoplanet research stands on the brink of even more exciting discoveries. With advanced telescopes, both on the ground and in space, we are entering an era where we can potentially detect biosignatures on distant worlds, directly image Earth-like planets, and perhaps even find evidence of other technological civilizations. Dr. Lisa Kaltneger, director of the Carl Sagan Institute, offers an inspiring perspective on the road ahead. Every discovery in exoplanet science brings us closer to answering humanity's most profound questions. Are we alone? How common is life in the universe? The next decades promise to be transformative, as we gain the ability to study the atmospheres of rocky planets, search for signs of life, and perhaps even glimpse other Earth-like worlds. This journey of discovery connects us to our cosmic roots and ignites our imagination about what, or who, might be out there. The story of exoplanet discovery is far from over. It is an ongoing adventure that continues to challenge our assumptions, expand our knowledge, and inspire wonder. As we peer into the cosmos, we are not just observing distant worlds. We are gaining new perspectives on our own world and our place in the vast cosmic tapestry. The journey of exoplanet discovery reminds us of the power of human curiosity, the importance of scientific inquiry, and the endless wonders that await us in the cosmos. And you, which exoplanet discovery did you find most fascinating? Share in the comments. If you've been amazed by this cosmic journey, don't forget to leave your like, subscribe to the channel, and turn on notifications for more astronomical adventures. The field of exoplanet research is constantly evolving, with new discoveries being made all the time. By engaging with content like this, you're not just learning about distant worlds. You're becoming part of a global community of space enthusiasts and citizen scientists who are passionate about understanding our universe. Liking the video. Your like helps boost the visibility of this content, ensuring that more people can learn about the exciting world of exoplanets. It's a simple way to support the spread of scientific knowledge. Commenting. By sharing your thoughts, questions, or favorite discoveries in the comments, you're contributing to a broader discussion. Your perspective might inspire others or even spark new ideas for future video topics. Sharing the video. When you share this video with friends, family, or on social media, you're helping to spread awareness about exoplanet research. You never know who might be inspired to learn more or even pursue a career in astronomy. Subscribing to Exploring the Universe. By subscribing, you'll stay up to date with the latest discoveries and insights in exoplanet research and astronomy. It's a great way to continue your journey of cosmic exploration. Dr. Neil deGrasse Tyson, a renowned astrophysicist and science communicator, often emphasizes the importance of public engagement with science. The day we stop exploring is the day we commit ourselves to live in a stagnant world, devoid of curiosity, empty of dreams. By engaging with and sharing content about exoplanets and space science, you're playing a crucial role in fostering curiosity, inspiring the next generation of scientists, and keeping the spirit of exploration alive. Remember, every star in the sky could be the sun of another world. The universe is vast and full of wonders, and there's always more to discover. Your curiosity and engagement fuel the ongoing journey of cosmic exploration. So, take a moment to like, comment, share, and subscribe. Join us on this incredible adventure as we continue to explore the universe, one exoplanet at a time. Until the next video, keep looking up and wondering about the possibilities that await us in the cosmos.